Okay, here we go. All right, this part of the video is going to go into transmission line resonators. As you can see, I started us off. This is page 278. A lot of this comes straight from the textbook, just so I can keep consistent with the same terminology and variables. So today we're going to talk about, or in this video specifically, we're going to talk about quarter, half, short-circuited, and some open circuit half-line resonators. I will try to go through this as intricately as I possibly can, and I will try to break this up into a few videos depending on how long these take. So initially we're just going to start off with the short circuit half wavelength line. So we will start there, and one of the things that you're going to need to see is what this means. On Canvas I will have uploaded a MATLAB script that should show you an actual resonance transmission line for n equals 1, 2, 3, and 4, and it should show the animation for each one of these depending on if it's short-circuited half wavelength, short-circuited quarter wavelength, or open-circuited half wavelength. So starting off this, we will need to go through some plots, and this is what you'll see online. You will see a transmission line with your voltage output as 0 being here, and you will see a line for n equals 1. I can show you n equals 2. I would say just run the MATLAB script to see n equals 2. This represents a transmission line coming in. So we have some input impedance, and this is going to be obviously a short-circuited input impedance line that has some characteristic impedance, some beta, and some alpha. So we're going to do some dealing with propagation constant, attenuation constant, and the characteristic impedance, and finding the input impedance. So we're going to be looking for all of these numbers for these transmission lines, either equation wise, and then we'll show you, or I'll show you some examples. So again, resonant frequency is based at omega equals omega naught. So that is the criteria we're looking for to attain resonant frequency. And we're going to say for this, the length of the line is just L equals lambda over 2. The reason I'm just writing this out is because later on when we get to quarter wavelength and then open circuit half wavelength, we're going to just replace these later on. So we're going to start by saying our characteristic impedance is equal to this Z naught term, and this is hyperbolic tangent alpha plus j beta times L. And the reason we're using hyperbolics is because we're not considering lossless right now. And then we're going to go through and do some some trig functions that are going to happen, and we're going to say this is equal to Z naught, and this is hyperbolic tangent alpha L plus j tangent beta L over 1 plus j, and this is, sorry, my j's are a little short, and this is tangent beta L times tangent hyperbolic tangent alpha L. So this just takes some trig functions and some trig identities to get there. Now alpha equals 0 if lossless, okay, and therefore if it's lossless, Zn will then equal J characteristic impedance tangent beta L. So that's the lossless case. In practice, we tend to talk about low loss transmission lines. So because, well, we want low loss. So that's really something we're always aiming for. So for this, we're just going to talk about low loss transmission lines. And this is where we can assume, for low loss, we assume, let's see, alpha L is much less than 1. Okay, so therefore our tangent, our hyperbolic tangent for alpha L, therefore is approximately equal to alpha L. So it's not lossless, so it's not 0, but close to 0. And then for this, now we want to apply, let's fix that. Let's apply omega equals omega naught plus some differential in omega, some small near resonance. So what we call this is near resonance. Okay, so we're trying to take a look at the resonance frequency and then just do some little bit of deviation from that resonance frequency and see what happens. And then so small delta W's, okay? We also need to assume that this is a TEM line, meaning it has electricity and magnetic properties. So TEM, not TE, not TM, but a TEM line. All right. Then we have, for that, we end up with beta L equals omega L over our phase velocity. And this is the phase velocity of the transmission line, which then equals omega naught L over our phase velocity plus our delta omega L over our phase velocity. So we're just trying to break this up and replace this omega in here with some characteristic, our resonance frequency, and some standard deviation away from that resonance frequency. Okay, so as I'm going, I'm going to kind of work my way this way, and so I'll erase some as I go, so I'll leave some old stuff up there, and you can see it. I'll try to break it up into 3 this time, unlike the last videos where I had 2 halves. And then this way, you'll be able to see some of this stuff as I'm working through it. And I can reference some things. So, went through that, we have that. Now we need, because we're dealing with a L equals half wavelength, we need to state this as pi phase velocity over omega naught. Okay, so this is true for omega equals omega naught. And now, for omega equals omega naught, we need to now state that beta L is equal to this pi plus this delta omega pi over omega naught. So we're applying these conditions to beta L in order to get a new beta L. All right, now we're also going to state that tangent of beta L is then equal to, we're going to take this and put it inside the tangent, and we're going to state this, and I'm going to do this real quick just because tangent of pi plus delta omega pi over omega naught. Now we break this up and we get that tangent of pi, which is just 0, so we're going to deal with just the equal sign here is tangent of delta omega pi over omega naught. Okay, and then we're going to say, because the standard deviation is so small, this is approximately equal to just delta omega pi over omega naught. So it's a nice simplification for this. this workaround. Now we have a new characteristic or input impedance, I'm sorry, not characteristic, input impedance, which is approximately equal to the characteristic impedance times this alpha L term plus this J delta omega pi over omega naught. And then we end up with 1 plus in the denominator, J times delta omega pi over omega naught, and then times alpha L. So this is kind of streamlining all of this and kind of narrowing all of this focus down. After that, we need to compare this to our regular characteristic impedance. So we're going to state that this equals, and I'll erase this real quick so we can keep working on this. And this takes a minute to erase. So then from here, we're going to go over to and say this is approximately equal to, this would be characteristic impedance times alpha L plus J delta omega pi over omega naught. And this is for since, and this is consequence, so since delta omega L over omega naught is much less than 1, we can use the form, we need to use the form Zn equals R plus 2J L delta omega. Okay, this looks familiar, right? So this is the input impedance of a series RLC circuit. Okay, so this is how we define that in the previous lecture slides. So when comparing this to this and looking at all of these and trying to get a feel for what all of this means, we can break out R, L, and C components from this. So our RLC components are, R equals Z naught alpha L. Our L is equal to Z naught pi over 2 omega naught. And our C term is therefore 1 over omega naught squared L. So we need to work out some more details for this. One, because what are we looking for this? We're looking for all of our components and our Q factor, really, in the end. So for this, the resonator resonates, okay, the resonator, let's just state it resonates at this is delta omega equals 0. So that would be the narrowing, and when that's equal to 0, and that would be L equals lambda over 2. Okay, so our half wavelength. And this is for n equals 1, 2, 3, dot, 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 all the way down. All the resonant modes. So if you go back to the MATLAB script I put in Canvas, you will be able to change these. I only added up to 4. I could have changed it to add up as many as I want, but I think you get the idea, up to 4. So one note for all this, and this is an important note. Resonance occurs, OCCURS, yeah, I think I got that right, at L equals n lambda over 2 for any n, for all n for n equals 1, 2, 3, ... resonant modes. So that's just a quick way of stating that up there. So these are the resonant modes. The unloaded Q factor this is our Q naught factor. This is equal to omega naught L over R. And this is then therefore equal to pi over 2 alpha L, and is beta over 2 alpha. And since this is true, since beta L equals pi for the first resonance. Sorry, my handwriting's desktop's getting in the way. I'm trying to move this. Okay, so these are the answers these are the equations we're looking for, and we can apply them later. So we will apply them to a coax line to start. So I'm going to move on into this, and let's make sure this is 16 minutes so far, so we're doing good on time. I will keep going with this and do example 6.1 from your textbook on the board in this video, so we can just apply this directly to that video. And then I will pause or stop the video and start a new one so we can go on to the quarter wavelength transmission line resonator. Let's clean this up. Okay, so from example 6.1 in your textbook, and feel free to follow along in your textbook. This is a pretty good example, and I'm going through it just as it is in the textbook. So example 6.1, and this is, we are looking for, we're trying to find the Q. Let's make sure we can, there we go. Trying to find the Q factor of the half wavelength coax line resonator. Okay, so that's what we're looking for in this one. There are some assumptions that are made. Let me see if I can see this better. Actually, that is a little bit better. So we can make some assumptions about this, and this is all from the text. So it's going to assume a copper core and an outer conductor, and we want the frequency to be 5 gigahertz. And we're going to compare the dielectric in the middle of an air versus a Teflon core, or a Teflon dielectric. So let's make sure we write this all out. So we're going to write some assumptions. So we're assuming copper core. With a radius equal to 1 millimeter. Okay. And then we're going to say an outer conductor. That one is R equals 4 millimeters. And then our frequency that we're looking at is going to be 5 gigahertz. And we're going to compare air versus Teflon. Okay, looks good. So some details. So we have our 2, this is A, this is B, and so A is our 1 millimeter and B is our 4 millimeters. And then we're looking at this between here, this is the air versus Teflon. Okay. Some important numbers that we're going to need. So we need sigma for copper. This is found in Appendix F. And this is 5.813 times 10 to the 7 Siemens per meter. We also have our air and our Teflon numbers, and air is epsilon r equals 1, and our tangent gamma is 0. For Teflon, epsilon r is 2.08, and our skin depth is 0.0004. That's a 0, and that's a 4. Okay? So that's the details we need, and the next we need to solve for some problems, or solve for some parameters. Okay, we need to find the surface resistivity at 5 gigahertz. Remember, this changes with frequency, so we need to understand what it is at the frequency we're looking at. So we need RS, surface resistivity, equals the square root of omega mu naught over 2 sigma. Okay, and this is equal to 1.84 times 10 to the minus 2 ohms. Okay, now in order to work any more details out, we need to find the attenuation due to the conductor loss for both the air and the Teflon. And then we'll need to do the dielectric loss. Okay? So, we need... Let's look at attenuation due to conductor loss. And that equation is alpha C equals RS over 2 eta ln of B over A. And this is times 1 over A plus 1 over B. So that's the equation we're going to use. And all we're doing is plugging numbers in already that we already have. And so we're going to look at air. So alpha air. Okay. Well, I'll leave it this way. Your textbook leaves, it doesn't subwrite it. It just says air. And then it goes alpha C. However you want to write it to understand it. So RS, we already have that. That's 1.84 times 10 to the minus 2. And then these numbers are 2. And if you remember eta, that's 377. And then this is ln of B over A. And so that's just 4 over 1. So 0.004 over 0.001. So it's essentially ln of 4. And then this is 1 over 0.001 plus 1 over 0.004. And we end up with an answer of 0.022. And I think I might be able to write a little further over here, but it's actually in Nepers per meter. If you, I wrote a little too big. I'll write smaller for the next one. And then we need to look at Teflon. And this one is alpha C equals 1.84 times 10 to the minus 2. And then for this, the Teflon has a 2.08, right? So that's my epsilon R. Remember, this is air has epsilon R of 1. And so we need to add the epsilon R of 2.08, the square root, over 2 times 377 times the ln of 0.004 over 0.001. And then again, 1 over 0.001 plus 1 over 0.004. And that is going to be 0.032, and again, Nepers per meter. Right? So that is our attenuation due to conductor loss for both air and Teflon. The next step is to attenuation due to dielectric loss, and we need to do that for both air and Teflon. Well, the air one is actually fairly easy, so we'll start with that. And if you remember, when we're talking dielectric loss, this is alpha. Your conductor loss is alpha C. Your attenuation loss due to dielectric is alpha D. I am going to leave this side up and erase this side because I want to keep these numbers here. And just look back at your notes for what you calculated, but I want to leave this stuff up because that's the problem that we're looking at. Almost wish I had a full wall of this. So then attenuation due to dielectric loss is therefore for air, right? So we have alpha D, and that one's 0. Okay, so there's no attenuation loss for air. But Teflon is a little different. We have alpha D equals this K naught square root of epsilon R over 2 times this tangent gamma. Okay, if we remember this from what we did a few weeks ago, that was the equation we came up, and we still, see, he did need it. So then this is equal to, K naught is 104.7, and then we have our epsilon R, which is the square root of 2.08. And then we have a times tan D, which is 0.0004. And this is all over 2. And then this equals 0.30. And this is in Neppers per meter. And lastly, the last thing we need to do is the unloaded Q values. We need both for air and Teflon. Okay, so unloaded Q are, the unloaded Qs are, say Q for air equals, this is beta over 2 alpha. And this is just, we already calculated beta. Right, and so this ends up being 104.7 over 2 times 0.022. Ooh, wrong parenthesis spot down there. And that is 2380. And then we have Q for the Teflon. And that is 104.7 times the square root of 2.08 over 2 times 0.032 plus 0.030. So when we're doing this, you have to make sure you add in both alphas, which equals 1218. So it has a lower Q value. So the Q of the air-filled line is almost twice the Teflon filled. Okay, so that is how you calculate your Q factors. You have to take into account all this other little stuff. Yeah, so pretty nice example problem. I like it. The next thing we're going to talk about is our quarter wave short-circuited transmission line. We're going to make sure we talk about all the different parameters in that. This one will be a little faster since we've been through it once. We're kind of just filling in the blanks, applying a quarter wavelength instead of half wavelength. And in the MATLAB script code, you should be able to just change that in there. I think I added it so you could just straight change it from quarter to half wavelength and look at the differences. One, just so you can see what we're doing. So let's